Thank you everybody for joining Water Wednesday. My name is Sen Kwang Si. I'm a Community Affairs representative at EBMUD. Main breaks are dangerous, difficult, and dirty. They can significantly affect the water supply for a whole neighborhood for hours. Crews must respond quickly, working through the mud, debris, and fast-flowing water to discover the source and make the repair. We are here tonight to dissect what happened to a main break. Along the way, we invite you to ask questions. If you move your cursor towards the bottom of your screen, you will see a Q&A icon. Click on it and type your question in the window when it opens up. We will answer as many questions as we can at the end of our presentation. I would also like to remind everyone that we are recording this presentation and we'll upload it to EBMUD's YouTube channel. You will be able to view it later by searching EBMUD Water Wednesday. Our speakers tonight are Mark Carradine, Manager of District Maintenance and Construction. He belongs to the Maintenance and Construction Department in charge of hundreds of employees who are responsible for the maintenance and repair of pipelines. And also David Kassoff, he is a senior civil engineer in charge of pipeline rebuild. He and his team are responsible for managing and designing pipeline infrastructure renewal projects. We will start with Mark.
Thank you, Sun Kwan. I would just like to say good evening to everyone that's joined us in this webinar. I would like to start by going over an overview of the process that starts the anatomy of a main break. Okay, so what I'm going to do is talk about our distribution system, give you an overview of that. What is a main break? A definition that it's by the American Waterworks Association. Types of main breaks that occur. Conditions that cause a main break. Continuous operations, which is one of the work units that we have. Investigations. How we go about finding and determining if we do have a main break, and share with you that all main breaks are considered emergency repairs, and I'll explain to you why later on. How we prioritize our leak repairs. I'll show you some impacts on catastrophic failures, and then I'll walk you through repairing a main break, and then I'll talk a little bit about proactive and preventative maintenance, and then I'll show you an unusual break that we had earlier this year, somewhere late summer. So with that, next slide. The distribution system. EBMUD serves 2 counties and 29 different cities, and that's from Crockett south to the unincorporated sections of Hayward, and from Alameda east to Walnut Creek and portions of San Ramon. EBMUD Distribution Maintenance and Construction Division has 5 work units, which are responsible for the investigation, inspection, and maintenance of 4,200 miles of distribution pipeline. And in that, we have 60,000 plus service valves and approximately 31,000 fire hydrants district-wide. Next slide. What is a main break? The American Waterworks Association defines a water main break as a failure in a water main that allows the escape of water and may allow the entrance of soil and other material into the pipe. This is true in some cases. As EBMUD, about 90% of our main breaks that we have, we never reduce we throttle the main down, but we never have negative pressure. We always have positive pressure on the main. And so therefore, there's really no chance of any kind of contaminants or soils or anything getting into the pipe. So we're very careful in terms of how the process that we take in terms of making repairs. Next slide. So these are some of the types of water main breaks. If you can see on the top, that's a full circumference break. And over to the left, you also see how the pipe broke. That's typically done through movement of the ground. And then you have below that is a longitudinal split, which sometimes it can go from one end of the pipe to the other. And since they are put in sections, that would be probably the only section that And sometimes our pipes are up to 20 foot in length. Okay, so that's typically done through corrosion or pressure spikes in the main. And then below we have damage by others and pinholes from corrosion. So the one in the middle, which is one that was probably caused by damage from someone digging or excavating around our utility and didn't exercise the caution to make sure that there was another utility daylighted before they actually continued to dig down. To the right of that is a picture of a still water main where corrosion has taken control of the pipe and allows for a leak through small pinholes. Okay, next slide. So what can cause a main break? So corrosion from the soils. We have ground movement, I talked about that. We have pressure surges, sometimes dramatic change in temperature, pipe life expectancy, and damage by others. Next slide. So in the process of identifying leaks, we have a continuous operations work unit, and that's 24/7. So through our continuous operations, we receive about 13,000 calls annually, and 1,100 shutdowns. We have about 1,400 road closures and 300 hit hydrants, fires, and notifications. This is the work unit that really is our contact to the public. Next slide. So what happens when a call comes into our dispatch center? Basically what happens is we dispatch an investigator and they go out to the site, and what they do is they identify if there's a water source. And if they can identify that it's potable water, then they set up BMPs. BMPs are best management practices, and that's basically sediment control, because we can't allow water to go into the creeks and streams. So, well, we allow water, but we can't allow sediment. So we put up dams with sandbags to control the sediment. We also control the flow of water. We assess the severity of the situation, and we call for resources, and we set up site controls. Next slide. And so all main breaks are defined as emergency repairs, and the reason why they are is because they are subsurface leaks. We have no idea of what's taking place underneath the ground, other than we know that there's signs of water through our acoustic devices. They worsen by the moment. They cannot be controlled. You can only monitor them. They are reactionary and scheduled. They are not planned events. They have the potential to destroy public and private property, as well as destroy streets and roads, and can harm fish and wildlife. Over to the right, what you'll see is that there's a priority. So I'm going to date myself here, but if you ever watched the show of MASH, the 4077 MASH, all of the patients or the wounded that came in, they were treated on triage basis. So this is basically what we do. So if you look down at the picture on the bottom left, you'll see this is what we prioritize as a P5 leak. We have to respond with that immediately, and we're required to fix that within 24 hours. Next to it is the P4 leak, and that is, I know the picture is somewhat small, but if you can see off in the distance, you'll see like a glare, and that glare is water that is surfacing. Okay, that is a P4, and we must be completed within 7 days to have that work. To have that leak repaired. But if you can see, because it doesn't require the attention as the one on the left, what we do is we'll schedule it and get to it within 7 days. And so we take the most severe, and then we work our way down to the least severe. Now, our P3s are the leaks where water typically doesn't surface, but we know through our leak detections, certain means that we have where we use acoustic devices, that we listen to the activity that's on our infrastructure, that we can tell there's a leak there. And so what we do is, if you can see the white paint in the ground, on the ground, we'll set it up for, we'll call for underground service alert, which is a requirement. It's a government code 4216, which requires all facility owners to identify and locate their utilities within a public right of way. So when someone is excavating, that they don't work into harm's way. And so the requirements on USA marking is you can't dig within 48 hours. So typically it takes about maybe 3 days before you're able to excavate. And that's when, if you notice that, if you ever had some work done on your street, you'll see a bunch of color paints like yellow, white, blue, and red. Those are all the utilities that are marking out their infrastructure. Next slide. So this is examples of catastrophic failures. On the top, that's Seminary Avenue in Oakland, which was a 6-inch cast iron main that actually broke. And then below that, there was a 6-inch main there, and that was on a court in McLeod and in Danville. You can see the damage that takes place when it's a catastrophic event. All the work and the restoration that has to take place in order to be able to get out there first and actually start to perform the work. So these things can be could be a big risk to the public and public safety. Next slide. So this photo is of a recent main break we had that was on Hiller Road in Oakland, and it's a steel main, and it's about 13 feet deep. And as you can see, the complexities of actually working to maintain or to repair a water main, because water just erodes anything that comes to it if it has pressure, right? And so the main was 13 feet deep here to the top of it. So in order to get down, we had to excavate, and the ditch kept caving in. So basically what is captured here is that mains are lengthy and disruptive, okay? And you can see from the picture, the nature of this work is inherently dangerous. You can't go into that ditch until it is properly shored, okay? It requires critical thinking, emergency preparedness, and expert skills to execute a repair effectively. Next slide. This is continuing on the emergency repairs. And this particular one, which is the same repair that I just showed a second ago, this is the shoring system that we had to install within the ditch, and we had to build back around the road around it in order to ensure safety while we're in it to make any repairs. We actually had to take out 200 tons of soil for this particular repair. Next slide. So this is so in order to complete this repair, we had a welder who had to weld new steel over the controlled section of pipe. Afterwards, we have staff, which are distribution plumbers. They will complete the repair after the welding by mortaring the pipe, and after that, then they remove the shoring and backfill the ditch, and then paving will come in. But as you can see, I mean, this is basically a 10 by 10 steel box that it's about 16 feet deep, and to allow for staff to go in there and to repair or to be safe while they're repairing the main. Next slide. Now, this is some of the equipment that we use or techniques in terms of excavation. On the left, you'll see a backhoe in the distance. You'll see a service truck and a truck. And so this is basically how we perform most of our excavations 90% of the time. Over to the top right, you'll see the guy standing around with a big tube into the ground, and that's what you call a vacuum excavator. This is when there's not a lot of room within the ground because you have conflicting utilities around. So what we'll use is the vacuum excavator to actually vacuum out the soil around all the utilities so that we don't risk danger of actually digging into another utility. And then below it shows where we have an excavator, which is larger excavation equipment where we use to dig bigger trenches at a more faster pace, and we also use to lift and to lower large size diameter pipes. Next slide. Okay, these are some of the fittings that we use in the repairs. So earlier I showed you there was a full circumference break. So this is a full surface clamp. If you look to the right, that clamp will actually fit over this pipe. We tighten it down according to your manufacturer's specifications, and then at that point the leak stops. Now note that I mentioned earlier on that because we do not like to reduce to have negative pressure on the main, water is actually coming out of the pipe as we're actually making the installations. But we have rain gear on and we're protected from the water, and the ditch is usually short, so it's okay to perform the leak this way. But also it helps to maintain the integrity of the health of the pipe inside the water. Okay. Below, what you have is, to the right, you have what we have is the flex coupling. This happens, we use these fittings whenever we have to cut in a piece. So if you notice on this is what you refer to as a longitudinal split. So we have to cut the pipe, move that section out, and install another section of pipe. And in order to do that, we have to use the two couplings to be able to connect that pipe together. And they are actually restraint couplings, so it helps to hold the pipe in place. Next slide. So now we move to the area of proactive and preventative maintenance. What I mentioned to you before, and in several slides back, there was a picture of a street that had no water surfacing, but you had marks, and I explained the USA marking. Well, in situations like that, where what we do is we try to be proactive about water loss. And so we have a program which is leak detection. And so what we do is use digital technology to go ahead and try to identify leaks in areas where we believe may have leaks, or we also have this technology installed by creeks and in areas of, again, where we know that we have a history of leaks. And so those things are loggers. They're devices that actually go on top of that goes on our water valves, and there's algorithms that they read to identify activity on our system. And then the other ones are nodes, and those are actually installed on hydrants, and those actually, they book in creeks so that we're able to tell if there's a leak anywhere near a creek. It's because we want to make sure that we have those fixed. And the other thing that we do, we go out and we have satellite imagery where we'll receive thousands of points of interest where we believe there could be leaks. And what we do at that point, we go out and we do foot surveys of the areas to identify if we do have a leak. And we use acoustic devices to what we call sounding the main to listen for activity, to confirm if those points of interest actually did produce or identify a leak. Below that, which is our preventative maintenance, we have a valve maintenance program, which we strive to inspect up to 10% of our system valves annually. We also have a hydrant inspection and maintenance program, which we try to inspect up to 10% of our hydrants annually. And then we have a cathodic protection program, which to try to extend the life and to extend the life and guarantee to ensure that the material that actually runs the course of his life, we actually install cathodic protection in forms of what we call anodes. And what the anode does is that it absorbs the electrolysis that comes through the soils, and it takes it away from our services. And then we have a pipeline replacement program, which is annually we try to, our goal is to replace 22.5 miles annually. That's our goal now. Next year it'll go up to 25 miles a year, but I'll allow David Cassett to talk about that during his presentation. Next slide, please. So this is the unusual repair I was talking about earlier. And so this is our Sequoia Aqueduct. This is what you would refer to as a trunk line, and this provides most of the supply or transmission south of Oakland. And so earlier this year, we identified a leak that was on it. In preparations to make this leak, we had, to repair this leak, because the impacts would have affected 300,000 customers. So in order to not impact them, because we didn't know if it was going to take us a considerable amount of time actually to have this, to have the line down while we make the repairs. So what we did was we brought up online an additional treatment plant to make sure that we had the adequate amount of service for those customers, so that they wouldn't go out of would be without water. And so again, this is our Sequoia Aqueduct. It's a 48-inch transmission line, and if you can see where the hand has a glove, that's a bottle, a glass bottle that's right there. Somehow the pipe was damaged. We don't know by who. We tried to look for records, historical information, to find out if there was any work done there, but we couldn't find anything. But yeah, there was a bottle into the pipe. Next slide, please. And you can see the bottle was brought out. The next slide. And so this is a large chunk of concrete. So basically what happened, and this is what we assumed, is that when the leak was created, there was a little piece of rubber that was put inside the hole, and then the bottle was actually kind of wedged in there, and then they poured this big old chunk of concrete on top of it. And surprisingly, it held for, we would imagine it was a long period of time, but then it finally surfaced. And so this is what we found. Next slide. And so when we removed it, we exposed the pipe to make sure that this was the extent of the damages. And what we did was we put a redwood plug in there to stop any more water coming out. Next slide. And so after that, we cut these bars that went across the pipe. And these bars are there because the pipe itself is actually thin metal. It's the bars that actually embedded in the concrete that actually provides the stability of the pipe to be able to endure the weight of the road and everything that travels onto the road. And on top of that, what you'll see is a coupling, and there's a plug in it. So this is one of our typical repairs on a steel main with a small leak. Next slide. And after that, we reinstalled or replaced the bars to make sure that we do not compromise the integrity of the pipe. Next slide. And then after that, we actually remortared. Well, it's actually concrete. So then they poured concrete and finished it, and that was the end of it. It's a very unusual repair on a leak. Next slide. And that's the end of my presentation, and thank you very much. But that is the anatomy of a main break. David?
Thank you, Mark. Good evening, everybody. Again, my name is David Katzev. I'm a senior civil engineer, and I'm in charge of the pipeline rebuild program. So, you know, the main goal of what we have to do within pipeline rebuild is to reduce the amount of work that Mark has to do in the field repairing main breaks. So as you can see, the second bullet there is to reduce main breaks. One of our main goals there. And in doing so, we ramp up to a sustainable long-term replacement rate. We do it with teamwork, research, innovation. We're trying to make process improvements in everything we do. We just don't want to double, triple, quadruple the amount of staff, the amount of work. We want to find new ways of doing things to improve our work, and then leverage that, implement it on a wide scale. We've been doing pipeline rebuild now for about 10, I think we're coming up on our 10th year. And I'll get into a little bit more detail now as to what it all means. Next. So, Mark was talking about main breaks, causes and failures. And just to review, that we've got ground movement, corrosion, pressure that he talked about. It causes different types of breaks. You can get a pretty big blowout, catastrophic break. The pipe can break, around the whole circumference. Longitudinally, it can split. We take all of that data, we capture it all on an annual basis, and we assess it, we evaluate it, we consider it when we're actually putting together our plans and designs for new replacement projects. So the data that's collected in the field by Mark's crews, they log everything in terms of what type of break it is and what the cause is. We take that data and make data-driven decisions based on what kind of material and how we're going to go replace the main, so it doesn't happen again. Next slide. So a little deeper dive into our distribution system. This chart breaks down the different types of materials and what we have to really focus on. That red squiggly line that you see there at the top, that is the main break rate per 100 miles per year for our cast iron pipe. Cast iron's our oldest pipe. Doesn't mean it's our worst pipe. It is our oldest pipe, and it's the pipe that we have most in our system, and it's breaking at the highest rate. That's the pipe that we focus on mostly in terms of replacing pipe within our system. Next slide. So if we even dive a little bit deeper into the cast iron pipe, there was this chart shows all the blue columns there are years, and those are the miles of cast iron pipe that was installed in our system. We stopped installing cast iron in the mid, almost up to 1960. But the key point here is that between the mid 20s and the mid 50s, we had about 1,000 miles of cast iron pipe put into our system. During that time period, there was World War II, material shortages, and so the cast iron pipe went through changes. It evolved during that time, and the big change that was made because of the material shortages was actually the pipe wall became thinner than it was, in the early 1900s. So the dark shaded squiggly line on top of that is actually the main breaks per, it's the main break rate for those individual years. And you can see our worst pipe really is that pipe in the 1930s and 40s. Some of our best cast iron pipe doesn't break nearly at the rate as the pipe from the 30s and 40s. So, in the last 8 years, we've replaced more than 130 miles of pipe within our system, and the majority of that is cast iron from this time period. Next slide. So, the 130 plus miles in the last 8 years is good, but it's not good enough. This chart shows our main break. The red line is our annual main break. It's not coming down yet. So as I said initially, our main goal is really to reduce main breaks. So in the future, we're going to continue to ramp up our replacement rate. As Mark said earlier, our goal is 22.5 miles of replacements. So you can see in future years there, we're going up to 25. We're going to stay there for a couple of years, up to 27.5, and then we're going to get up to 30. You have to do it methodically. carefully. You have to hire new staff, purchase equipment. So you just can't ramp up super aggressively. And we'd rather take a more methodical approach to ramping up our replacement rate as we can monitor our main breaks in future years. So what do we do in design? We take all that data, the data I was talking about, the main break data, the failures, the causes, the types of breaks. We assemble all of that data, the pipe materials, the year of the install, the size of the pipe, the 6, 8-inch, 12-inch, 16-inch diameter. We take all of that data, the environmental conditions, we assemble it all into a package, and we actually apply machine learning to it. We look for trends, we look for patterns, we look to see where these pipes are breaking, and then we prioritize those replacements. We go after the worst pipes. We go after the right pipes to replace. And when we visualize the risk from the machine learning algorithms, the picture on the right there shows basically what we start with. And the red and the orange, that's our worst pipe. The red, we actually call it a grade F pipe. The orange is a grade D pipe. We cluster those together. We cluster those D and F pipes together when we're creating a project. So that's an example of a project. I don't have the limits of that project, but we went into that area and we replaced the pipe just close there to Lake Merritt. Our goals are designing, up to 30 miles of replacements per year. We have to stay ahead of our construction goals. We also prioritize coordination with cities and counties. Who else is doing work in the streets? Can we do this at the same time or before or right after? Can we coordinate? And then another really big piece of what we do is we look at paving plans. We have a whole GIS map of all of our pipeline replacement projects. From each city and county we work with, we have their paving plans and we overlay the two together. They don't always match, but when they do match, we will work as hard as we can to get in there and replace the pipe before the city or county paves the road. Another really key thing that we have to think about, and tomorrow, very appropriate, tomorrow's the great shakeout. We have the Hayward Fault that runs right through our system. And that picture at the right there shows a trace of the Hayward Fault running through our system. So we live in earthquake country, and I don't think I need to tell you all that, but that is a big hazard that we have. We also have landslides. We have land that's gradually moving. And then we also have liquefaction zones right next to the bay. We have a very complex geologic system within our whole service area. So when we're designing our pipes, thinking about materials, hazard resiliency is a priority that we have to think about. We want to think about putting pipes in the ground that are going to withstand any kind of movement and not break. So this next picture here shows two different types of pipe materials that we're using and installing in our system, a restrained joint ductile iron pipe and an earthquake resistant ductile iron pipe. These pipes, when you stick them together, they have very complex joints where they actually lock together. The earthquake pipe actually locks together, but then it can move back and forth within the joint, and then it can move up and down as well with different types of ground movement. We're installing the earthquake resistant ductile iron pipe in areas near or adjacent to the Hayward Fault Zone and in areas where we have a significant landslide. Now, when we choose these materials, we're actually quite careful in evaluating all the research and studies that have gone into making these materials. The picture on the left there is a picture from back at Cornell University where they actually simulate fault ruptures. There's actually a pipe underneath that grid soil that you see in the picture. It's filled with water, it's pressurized. They simulate a fault rupture, and they still see how well the pipe performs. So we take a lot of great pride, effort, thought into choosing the right materials. Again, to reduce main breaks, to put in hazard resilient materials. Next slide. And the last thing I want to talk about is that, that large scale fault rupture test from Cornell, EBMUD is now in partnership with UC Berkeley. We've actually moved that test apparatus from Cornell over to UC Berkeley, and we've created a pipe testing facility in collaboration with UC Berkeley. A couple of pictures on top there show actual tests that we've been performing at UC Berkeley on this earthquake-resistant ductile iron pipe. We're putting different types of stresses and strains on this pipe. We're using fiber optics to monitor all these different stresses and strains, really to ensure that we're putting in the best material that we can. The material that's going to be hazard resilient and the material that's going to last 100+ years. So we've done lots of different pipeline tests, and we're actually working with a lot of other utilities in California, Los Angeles Department of Water and Power, Metropolitan Water District, San Francisco Public Utilities, EBMUD. We're all in collaboration with the Center for Smart Infrastructure to really put together solutions to these big challenges that we have. And that is it for my portion. And I think Sun Kwong and Mark, we can go to questions.
Yes, thank you, David, and thank you, Mark. So let me stop sharing, and then we can go to questions. So our first question coming is asking about how is the quality age of our water pipes around the Bay Area? Is it PVC pipes or old iron pipes? What preventive maintenance schedule do you do on the water pipes? I think that you maybe touch on it, but do you have anything to add?
I can just talk about the pipes, and then I can let Mark talk about the preventative maintenance. I did have a chart there. I didn't review all the materials, but we have 1,300 miles of cast iron. We have 1,100 miles of cement pipe, asbestos cement pipe. We have about 1,000 miles of steel pipe. And then we have 400+ miles of PVC and some HDPE pipe. So we have a wide variety of pipe materials in our system. And in terms of preventative maintenance, Mark, I don't know what you wanted to add there.
Well, as far as preventative maintenance, the opportunities that we have to perform preventative maintenance on a water main, say a cast iron main, is if we do have a break. When we make the repairs, we'll install an anode, which is either magnesium, and that for that section of pipe, what happens is that anode will actually take the electrolysis from the pipe, so it helps to extend the life of the pipe. The other things we do is that we exercise our valves to make sure that they're working properly. But in terms of prolonging the life of the pipe, we do have electrolysis stations installed on the pipes to help prolong their life expectancy. So that's part of our preventative maintenance.
All right, so our next question is actually not a question, but a compliment. So they live in the El Cerrito Hills and near a known slide zone. So they have occasionally breaks and truly appreciate our crews work through the night so that they can have water service by the morning to have coffee and shower. And thank you for the service and all around. So for full disclosure, their families also have some connection with the water industry. So his dad is working in the LA Department of Water and Power and the State Department of Water Resources. So let me move on to the next question. So what material is used for the pipes today? They have seen redwood pipes near Hercules that was used for over a century.
So standard material right now that we're using is ductile iron. And as I showed a few pictures there, one of the restrained ductile iron and also the earthquake resistant ductile iron. That's our primary material for installation. We also have some plastic pipe that we're installing. There's a innovative polyvinyl chloride pipe, PVC pipe from Korea that we have piloted and researched. It was tested at Cornell University. It performed quite well under seismic loading conditions. So we're also installing some of that pipe. But our primary material of choice right now for distribution pipe replacements is the ductile iron.
All right. So this question is about who pays for the damage that these main breaks do.
Unfortunately, I think everybody pays for that damage as a part of your monthly payment for the services provided. That all goes into the equation of maintaining the infrastructure.
Mm-hmm. So if we can find the culprit, do we charge them?
Well, so if it's damaged by a third party, we do file claims against the third party. Yes, we don't. Case in point, and this is pretty interesting. If you're familiar with the Nolan Zoo, we just recently had a contractor. They're actually building a new structure in the elephants exhibit, and so they were actually doing some work, and they drilled down in one of our mains, and so we had to go up there and make a repair on that particular extension, and so we are providing them with a claim for the damages that has taken place. So if there is a third party, responsible party, we do file claims against them and collect.
Thanks. So also remind people, if you have any question, please type it in the Q&A box. So the next question is, Mark, you mentioned, and David, you both mentioned that pressure causes main break. Can you explain further?
I'll touch a little bit on it, and then David, you can add into it. I mean, sometimes there's pressure spikes within the system, which will create a break. Also, and this is something, whenever there's sometimes when operating a fire hydrant, if you shut it off really quick, you can create a water hammer. That's a spike right there, and it'll create a break. So there's just sometimes there's transient surges, pressure surges throughout the system, but we've installed some new technology to actually identify or to reduce those pressure spikes. So we're working on eliminating that cause of pipe breaks. David, you want to add anything?
Yeah, I mean, pressure over a certain area is a force, and so the higher the pressure, the greater the force, and so you can have conditions where the pipe is corroding, so the wall thickness is decreased, and you have high pressure over that area, high force, and the pressure is enough to just cause a break. So pressure alone just doesn't cause break. You need some other factors along there to add to it. And just to, when we're designing our pipes right now, we have pressure ratings of 300 plus PSI, and we don't see that in our distribution system. So the pipes that we're putting in right now can withstand any of the pressures that we have in our system.
Okay. So David, you mentioned corrosion, and then I think Mark, you probably also mentioned a little bit about our corrosion control, and then also with the managing our water quality. Can you talk a little bit more about our water is not corrosive? Or David?
You want to take that, Mark?
So are you asking if the water is corrosive? What question are you
So
asking?
we have a corrosion control, and then
corrosion control, yes.
Yes.
based on how we maintain the pH levels in our system, it reduces any kind of the amount of corrosion caused by the water. And so inside of our pipes, depending on the material. So, and I'm not sure if this comes in the ductile iron, but we have they're lined with a material to prevent from the water corroding the pipe on the inside. As long as that material stays in line on the pipe, it prevents the corrosion of the pipe. As far as soil corrosion based from the soils, whenever we get the opportunity, we'll either replace an electrolysis testing station or add anodes on certain sections of the pipe throughout the system to make sure that we are actually reducing the amount of electrolysis that are entering into the pipes. So we do that with service connections, and then we also do it on sections of mains where we're testing and we show that there's a little bit of activity in terms of corrosion.
All right.
Yeah, and Seung-Kwan, the ductile iron that we're putting in the system right now has a double cement mortar lining to minimize any corrosion. And on the outside, we actually coat it with zinc as a sacrificial anode to reduce corrosion as well. So we're looking at it from the inside and the outside.
Mm-hmm. So let us go back to the question about pressure. So how is the pressure maintained during the repairing, so that assuring that continuous service is for the customer and also preventing like contamination entering into the pipe, into the flow?
It depends on the type of break. So if it's a full circumference break, or even what we call a blowhole, what happens is we control the water flow through our valves, okay? And on that, what we do is we keep a certain amount of positive pressure, about maybe 5 pounds of pressure. That's enough pressure coming out of the pipe to prevent any kind of foreign matter from entering into the pipe, but enough water coming out so where it doesn't prevent us from making a repair. So that's how we're able to maintain the disinfection of the pipe. As far as service to customers, we're not always able to maintain an adequate amount of service to customers. So if we reduce the pressure down to about 5 pounds, it's probably not going to service everybody. So there will be a disruption in service, but typically that disruption is probably no more than maybe 4 hours. Okay.
Mm-hmm. So next question is for David. So you talk about machine learning. Are we using ChatGPT?
No, not yet. We could in the future. That's something actually we're looking into with UC Berkeley as part of some research and innovation in terms of using ChatGPT. But that's not what we're doing. There are standard algorithms in machine learning that look for patterns, that look for pattern recognition in data. And that's what we're doing as part of the machine learning.
Can you elaborate a little bit more on what kind of data that you look into or analyze?
So the data is well, you have the pipe size, the pipe material, the environmental conditions. If you do have soil data, you can add that in. If you have geologic data in terms of hazards, fault zone, landslides, liquefaction, you can add that in. You've got all the break data, the different types of breaks that are occurring. And we have data all the way back to 1990. So it's quite a bit of data to sift through and to use with these algorithms.
I see. So, so this question is asking about in the Napa and Sonoma area, do they have the same kind of pipeline failure risk as we are? Do you have any idea?
David probably would have some knowledge of that.
In the Napa Sonoma area, I mean, yeah, I'm sure there are definitely similarities. You know, geologic, the seismic, soil conditions. You know, Definitely similar conditions up there.
All right.
So
the next question is about why is it important to not allow water from main breaks to go into local streams to the creeks?
It disrupts the ecosystem for fish and wildlife. So basically, our water, we use chloramines, and so we have to dechlor the water before it goes in there. But sometimes it's not only the chloramines that actually can cause a risk to the safety of the fish and wildlife, but also the volume of water that is released into the waterways, like sediment, things like that. You can really disrupt it, and it offsets the balance of their ecosystem, so, or their habitat. That's probably about the best I can answer that question.
Yeah, and also we are a steward for our watershed resources, so that we are very careful about our water system and then any potential contamination to the our valuable resources. So what is the cost of a typical main break in damage and repair?
We had that number. We ran the numbers about a year ago, and it's about 19,000 per break.
Okay.
And
So
that was based on the number that I quoted earlier in terms of the leak repairs that we had in the earlier slides.
okay, so Mark, the next question is also for you. So when was the pipe that was patched with the bottle originally installed?
And I'm looking at that right now. It was installed in 1928.
Okay, so let me see. Are you able to do anything to prolong the life of the asbestos cement pipe? I think that's for David. Or maybe not.
you know, that, I mean, the one strategy I think that we've talked about and we've tried in terms of prolonging the life is to line it. And that's a trenchless rehabilitation method. And what that means is basically if you have a block of asbestos cement pipe, you excavate 2 pits at the intersections, and you can actually pull a structural liner inside the pipe that bonds to the actual asbestos cement pipe. That is going to prolong the life of the pipe. And we've tried that, we've piloted, we've been successful with it, and we're looking into do that more. You don't have to just do that with asbestos cement. You can also do it with cast iron. You can do it with steel. You can do it with other materials. But asbestos cement is the one area that we were focusing on earlier for that.
All right, so the next question is, are you able to do anything? Oh, I read that, I'm sorry. So the next question is talking about in Alameda. So recently they live in a condo complex and have a break due to tree roots that impact some of the homes. What priority would EBMUD assign to this?
Anytime you disruption of water service, that's a priority 5. Okay. And we typically, our investigations, we dispatch within an hour. Within an hour, an investigator is on site after the call comes in. And from that point, we still have to wait for emergency USA marking. So we usually give about a couple hours for PG&E to respond. We cannot dig prior to that. So typically, you're probably, I don't know, somewhere around 6 to 8 hours before water is restored. But that rises to the level of a priority 5.
Mm-hmm. Okay, so David, so you talk about the AC pipes. So is the management of the water quality and the pressure, can they also help?
Yes, yeah. Those are also solutions where we can decrease the pressure in some areas to extend the life of the pipe. And we are investigating that in some areas. So that is also a solution.
Awesome. So, David, do you have an accurate map of the different grade of iron pipes that were installed generations in the past? How often are the crews surprised by what they find in the ground?
Oh, that's a good question. So first of all, yes, we have a map of all of our pipes and all of the grades. So the answer to that first question is yes. Are the crews surprised, when they're fixing the pipe? Is that the second part of the question?
Yes, I believe so.
I'd say yes and no. That we have areas where crews go back repeatedly to fix main breaks, and those are the projects that we end up prioritizing in terms of replacement. So there's no surprise. Sometimes, yes, they are surprised by that. It could just be a small break. We tie into some pipe. We use what Mark was talking about in terms of a flex coupling, or putting in a new section of pipe to repair it. And the pipe actually that we're connecting to is in very good condition. So sometimes it can be a surprise that the pipe breaks.
Okay. So the next question is about what do the water tower contribute to the pressure of water to the home?
I'm not sure if they're talking about the location and the elevation of the reservoir in relation to where their home is. So our pressure zones are typically 200 feet in elevation from each other. And so based on the equation in terms of pressure, you're probably going to get anywhere between 60 to 80 pounds of pressure, and maybe even less than that. But if you're at the low end of the pressure zone, you typically have higher pressure than you are at the upper ends of the pressure zone.
Yeah, so we also have a more detailed question about pressure. So the question is there a target water pressure for our water distribution pipes, or is there a range for the pressures? So he is live in 1.5 mile north of UC Berkeley campus at about 700 elevation, and the strip pressure is about 130 psi, and with spikes to 170 psi, and it used to be even higher.
You want that, Mark, or you want me to do it?
You can, but I will say, like, a target ideal pressure going into a home is anywhere between 60 and 70 pounds of pressure. But go ahead, Dave.
That's on the high end, the 130 psi. So that's not something we aim for in terms of designing. We're more on the lower end, like as Mark was saying, 40, 50, 60 psi.
Sometimes it just depends on the terrain and the proximity of the reservoirs to the homes. And so if it's a hilly area, which he says 700 feet in elevation, there's probably sometimes you may get a little bit of high pressure in areas like that, because it's kind of hard, I guess, engineered to separate out the pressures between the two zones. That's probably about the best I can answer that question. I don't know about you, Dave.
Yeah, I mean, it's on the high end.
So I want to say that to respect everybody's time, so we are now at 7:01. Why don't we answer maybe 2 more questions? And I want to see the next question is for David. So can you elaborate on the electrolysis system? How does it work?
What's
electrolysis?
Yeah,
electrolysis. Thank you.
I guess that's just the corrosion when you create a corrosion cell, and the metal will the electrons move from one spot to another spot, and you actually lose material. So it's, it's how a battery works. It's the electrolysis process. So when corrosion sets up on our metal materials, the electrons are moving and you're losing material off the pipe. So the wall thickness decreases, and then that's when that can cause the main breaks.
Okay. So I think let us answer the final question on a note about safety. So there's a question about you mentioned that there's a lot of pipes is AC pipes, asbestos, cement pipes. Are they safe?
You want to take that, Mark?
I don't think there's any studies that have been shown to find that they're not safe. As far as information or data that is public. Other than that, I don't really have an answer for that question. But asbestos cement pipe has actually been in our system for over how many years, David? About since the 60s or early, I think late 50s and 60s, but there hasn't been any reports or any studies that's shown that the asbestos cement pipe is actually hazardous to your health. Now, when it relates to asbestos, it has to be friable, right, for it to actually be dangerous to or a hazard to your health, and that's from ingestion or breathing. But in this particular case, it's not friable, so that's probably about the only manner in which I believe that it is hazardous to one's health. But there was a couple questions that were in here that are really interesting that I would like to answer, if you don't mind, Sun Quan.
Yes, please.
Okay, so one of the questions was on contaminated soil. And what is our policy for dealing with contaminated soil from a non-EBMUD source when performing excavation? It just depends when you say a non-EBMUD source. If it's in a public right-of-way and it's our right-of-way or easement where our infrastructure is located, we have a database which has all the information about known and areas where there could be possible contaminations. So how do we deal with it? Before we make any excavation, unless it's an emergency, we do have areas where it's outlined, but before any of our projects, we receive soil analysis from our environmental compliance section. And that'll let us know how to handle the soil if there is contaminated soil. And there's levels of handling that we have based on the requirements that come in the soils report. The other question was, it had to do with the cost. Is there any way to are there ways EBMUD can reduce the cost of brake repairs? Does early detection or reporting helps? So I talked about this a little bit earlier in terms of what we do as our proactive maintenance, and that is our leak detection. So we invest a lot in leak detection. Like I said, that each year we'll get a satellite reading, and in that will be thousands of points of interest where it could be possible leaks that we cannot detect based on normal technology that we have. And then from there, we go out, we perform foot surveys. And if we detect that there is a leak, then we will repair that leak at that time. And what that does is that we can identify and make that repair before it caused any damage. That's one way that we reduce the cost. The other way is our pipeline replacement. And so as we start to install more resilient material, that will help to reduce the breaks that we have. So those are some of the ways that we are working to help prevent, to reduce the cost of main breaks.
Great. So,
Sun Quan, I'd just like to say, with the asbestos pipe, we
yes.
monitor the water quality, and we test it, and the water is safe. There's no asbestos. There's no asbestos in the water. So just to clarify that. And then also, I think there was a question about who teaches the UC Berkeley class.
Yes.
And that is we have a whole about 20 to 25 different, subject matter experts from East Bay MUD that go in to teach the class at Berkeley, from water supply to water operations, to maintenance, to pipeline construction, to water rates, to water policy, to sustainability and resilience. We have different East Bay MUD people that go in and lecture and teach the class, and then we take the students to our facilities on field trips, to the wastewater treatment plant, to the water treatment plant, to a pipeline construction site, to our watershed. So we're teaching the students at UC Berkeley about everything that we're doing at East Bay MUD. And, a lot of that's in hopes with a goal of exciting students to come into the water industry and to join us at East Bay MUD, or to go join a consulting firm to work on water issues. And so it's very rewarding. And we were in our second year of teaching this class.
Awesome. To prepare for our future workforce, I think that is a very important program. And then our district also extends to other areas. So we have apprenticeship and other programs that to help people about it. So with that said, I want to wrap up for tonight's Water Wednesday. I think we have some really great questions, and thank you, David and Mark, for your great discussion. I think that sentiment is also shared from the audience. They do actually comment on it. And I want to let everybody know that our last Water Wednesday of the year will be on November 15th. The topic will be about wastewater and its future amidst sea level rise and climate change. So stay tuned. Thank you, everybody. Good night.